And it's also useful in attaining, showing the existence of properties the other way around. Right? So if you have, for example, derivative going to j omega times the spectrum, then the derivative in the spectrum goes to minus jt in the time domain, and similarly for the others. Okay? And this is because of the symmetry of the Fourier transform and inverse Fourier transform formula. Now, one more is Parseval's relation. Okay, so we also had this for the Fourier series representation. Okay. So Parseval's theorem tells us that if you want to compute the energy in the time domain signal, this is actually equal to the energy in the frequency domain signal, scaled by this 1 over 2 pi. Okay. So this is straightforward to prove. Okay. So we can just start out from the time domain integral. All right? So here we're computing the total energy of the signal in the time domain. Okay? So you can write this as the integral of x of t times the complex conjugate of x of t. But instead of writing x of t directly, let me write it as 1 over 2 pi x j omega e to the j omega t d omega complex conjugate. Okay? So x of t absolute squared, you can write as x of t times the complex conjugate of x of t. Now, instead of writing x of t directly, I'm replacing x of t with its Fourier transform, with its inverse Fourier transform formula. Okay? Now let's interchange the order of the integration. All right, let's instead move this dt inside and d omega outside. Okay? And also when you get rid of this bracket, you need to apply this complex conjugate onto all these different terms. Okay? So you get 1 over 2 pi integral x of j omega complex conjugate x of t e to the minus j omega t dt d omega. Okay? So I'm moving dt inside, d omega outside. Right, complex conjugate moved inside gives you a negative sign in the exponent here, and also a complex conjugate on top of capital X. Okay? All right. Now, if you look at this, this integral inside is the Fourier transform of x of t. Okay. So this gives you capital X of j omega. Okay. So then you get the result. Right, this is 1 over 2 pi, the integral of the absolute square of the spectrum, d omega. So this is saying that if you want to compute the total energy of the signal, it is equivalent to computing the total energy of the signal in the frequency domain. Right? This is reasonable. Right? If you want to compute the total energy, it should be the same computing this in the time domain as computing it in the frequency domain. Okay? Now, when you say that this integral gives you the energy, total energy of the signal, then this absolute square of x of t gives you the energy at the time, instantaneous time t. All right, so this gives you, you can view it as the energy density at the time t. And energy density is power. right? So we view this as the instantaneous power, okay? Now, similarly, in the frequency domain, if you say that the total energy is the integration of these frequency components, absolute squared, then this absolute square of x of j omega, you can view as the energy density at the frequency omega, okay? So it specifies how much energy, right, how much energy is at or around this spectrum, this frequency omega. Okay. So we can view this x of j omega absolute squared as the energy density spectrum. Okay? All right. Now, knowing this property is useful because sometimes it's easier to compute the energy in the time domain, and sometimes it's easier to compute in the frequency domain. Okay. So we can look at an example of this. Okay. So here, suppose you're asked to find the energy of the signal x of t, okay? Now, you know that x of t has a Fourier transform that looks like this, okay? So if you want to compute the energy in the time domain, then you would need to first take the inverse Fourier transform of this signal and then take the integral of the square of that signal, okay? So for this signal here, right, you can view it as 3 rectangles summed together. So if you do an inverse Fourier transform, this will give you a superposition of 3 sinc functions. And then you take the square of the sinc functions and then integrate them. Right? This sounds like a nightmare, right? But by Parseval's theorem, you know that you can compute the energy from the spectrum directly, okay? So in fact, by Parseval's theorem, okay, or by Parseval's relation, E is equal to 1 over 2 pi, the absolute square of the spectrum, E omega. Okay? So we can actually split this into 3 parts, right? 3 rectangles. All right, so this rectangle gives you, square root pi squared, which is pi, right? So this is pi times 1 half. So this is pi times 1 half plus pi over 4 times 1 plus pi times 1 half again. Okay? So because this is square root pi, so the square of this gives you pi, and this is 1 half. Okay? So square root pi over 2, the square of this is pi over 4, times the duration, which is 1, right? And this part is the same as this, so it's pi times 1 half. Okay. So if you sum this up, this will give you 5 over 8. Okay? So what we're doing here is that we're computing the energy of these 3 blocks, right, separately. Okay? All right, so another useful thing, right? This is not necessarily related to Parsifal's theorem, right? But by what we learned, by the previous properties that we learned, right, we also can obtain an easier way to find the value of something like this, right? This is the derivative of a function x of t evaluated at time 0, okay? And assume that x of t has a spectrum that looks like this. Okay. Now imagine if you want to do this in the time domain. Okay? So if you want to do this in the time domain, you need to first take the Fourier transform of this, the inverse Fourier transform of this. This is two rectangular waves. The inverse Fourier transform gives you the superposition of two sinc functions. You take the derivative of the sinc function, and then try to find the value at 0, okay? So dealing with sinc functions is always a little bit tedious, right? But you can actually compute this value in the frequency domain, which makes it much easier, okay? So note that suppose we define g of t as this derivative of x of t. Okay. We know that the Fourier transform of this is j omega x of j omega. And let's call it g j of omega. Okay. Now what we're asked to compute is this d, which is g of 0. And g of 0, right, we can write as 1 over 2 pi integral of g times e to the j omega t d omega evaluated at t equals to 0. Okay? So g of 0 is g of t evaluated at time 0. And g of t you can write in terms of the inverse Fourier transform of capital G, okay? So I have the inverse Fourier transform of capital G evaluated at time 0, okay? So if I set t to 0, then what I have is just the integral of the spectrum scaled by 1 over 2 pi. Okay. Okay. And g of j omega is just j omega x. So this is 1 over 2 pi j omega x of j omega d omega. Okay? Now, x of j omega we have here. Okay, so it's equal to j square root pi between 0 and 1, and minus j square root pi between minus 1 and 0. Okay, so I just plug this inside, and this will give me 1 over 2 pi integral from 0 to 1 minus omega square root pi d omega plus minus 1 to 0 omega square root pi d omega. Okay? So I'm plugging in this j square root pi inside here. Inside here, right? Jj gives me a minus sign. Okay? And then I'm plugging minus j square root pi inside here, right? So minus j times j gives me a positive sign, so I get a positive omega times square root pi here. Okay? So if you work out this integral, all right, this will give you minus 1 over 2 square root pi. So through these examples, we're just trying to give you a sense of why we want to study all these relationships between the time and frequency domain. Right? Because sometimes signals are easier to deal with in the frequency domain rather than the time domain, and vice versa. Okay? So now if you know the relation between the time and frequency domain, you have the freedom of choosing which way you want to approach this problem. So in the second set of slides, right, for the same chapter, we continue with another very important property, which is called the convolution property. Okay? So the convolution property is useful for us to study the characteristics of a signal passed through a linear time-invariant system, right? Because we know that when you pass a signal through a linear time-invariant system, the output is equal to the convolution of the signal and the impulse response. Okay? Now, if we recall back to our study on the periodic signal x of t, right? Remember that for a periodic signal, we can always write it in terms of its Fourier series representation, which is basically a linear combination of these complex exponentials. Okay? Now, since complex exponentials are eigenfunctions of linear time-invariant systems, therefore, if you have a certain complex exponential coming into the system, you will have the same complex exponential going out of the system. And each one scaled by its corresponding frequency response. Okay? So a linear combination of these complex exponentials gives you an output that is the linear combination of the same complex exponentials, each one scaled by this complex frequency response. Okay. And we showed in previous chapters that this frequency response you can compute by taking the integral of the impulse response times e to the minus j omega tau d tau. Okay? So over there in the previous chapter, right, we just showed that this is how you can obtain the frequency response. But in hindsight, right, after studying this chapter, we now know that this form is actually in the form of a Fourier transform. Okay? So in hindsight, now we know that the frequency response is actually just the Fourier transform of the impulse response. Okay? So the Fourier transform, right, of the impulse response gives you the frequency response. Okay. Now, suppose we extend to aperiodic signals. Right? So suppose that x of t is some aperiodic signal. We know that we can write it in terms of this inverse Fourier transform of the spectrum. And the inverse Fourier transform of the spectrum is basically a linear combination of infinite frequency components. Okay? So this integral you can view as a limiting form of the linear combination of these infinite frequency components. All right? So if you view it this way, right, then the output of the system should be a linear combination of the same frequency components, right? Because these complex exponentials are eigenfunctions of linear time-invariant systems, each one scaled by the corresponding frequency response. Okay? So again, as you take omega naught to 0, this converges, okay, to the Riemann integral, which is 1 over 2 pi, the integral of x of j omega times h of j omega times e to the j omega t d omega. Okay? Now, if you look at this, this is in the form of an inverse Fourier transform. Okay? So when you say y of t can be computed from this inverse Fourier transform formula, then this is implying that x times h is the Fourier transform of y. Okay? So this implies that this x times h is the Fourier transform of y. Right. So this is what we just mentioned. Right? Suppose you let capital Y be the Fourier transform of y of t, then by the above observation, you can infer that the spectrum of the output, y, is equal to the frequency response, right, the Fourier transform of the impulse response, times the spectrum of the input signal. Okay? Now, y of t, right, the output of the linear time-invariant system, is equal to the convolution of the impulse response and the input signal. And we know that this convolution has a Fourier transform that is equal to the product of the spectrum and the Fourier transform of h. So this gives you a very useful property saying that convolution in the time domain corresponds to multiplication in the frequency domain. Okay? Now, up to this point, right, we have obtained this relationship through observation. Okay? But you can actually derive this more formally, right? More formally, starting, directly by taking the Fourier transform of this convolution. Okay? Now recall that, the convolution is just the integral of x of tau h of t minus tau d tau. Okay? Now I want to show that the spectrum of y is the multiplication of h and x. Okay? So this is the Fourier transform of y of t, which is the integral of the convolution between x and h. So this convolution is x of tau, h of t minus tau, d tau, times e to the minus j omega t dt. Okay? So this is the convolution, right, between h and x, which is essentially y. Okay? So this is the integral of y of t times e to the minus j omega t dt, which is the formula for the Fourier transform of y. Okay. Now, again, let's change the order of integration here so that we integrate over t first. So this will give you integral of x of tau, integral of h of t minus tau, e to the minus j omega t dt d tau. Okay. Now let's do a change of variable where we let t minus tau be replaced with t prime. Okay, so suppose we let t prime be t minus tau. So this gives me h of t prime, okay, e to the minus j omega. Now when I do this change of variable, t becomes p prime plus tau, okay? Now let me just leave one of the t primes inside. So I get e to the j minus j omega t prime, dt prime, and then leave one outside. Okay? And the reason for that is because now the integral inside becomes a Fourier transform of the impulse response h, right, which gives you the frequency response. Okay? And if you bring this outside of the integral, you have the integral of x times e to the minus j omega tau d tau, which is the Fourier transform of x. So eventually, this gives you h of j omega times x of j omega. Okay? So through this derivation, we have officially showed that convolution in the time domain corresponds to multiplication in the frequency domain. Okay? And this is probably one of the most useful properties, right? Because convolution is usually very tedious to compute, right? So you may have seen that through your homeworks and exams, right? Convolution is usually tedious to compute. But now you know that convolution in the time domain simply corresponds to multiplication in the frequency domain. So now you're capable of first converting this to the frequency domain, performing the multiplication, and then transforming it back. And that is often much easier than computing the convolution directly. Okay? Right, and we actually have an example of that, but I'll leave that for next time. Okay, so the TA wants to hand out the midterm. So please just take a look， 就是看看有没有什么问题啊，有问题的话就是立刻问助教。那看完以后要把考卷还给助教，才可以离开。